So Dr. Michael Tayler, he's at the Barcelona Institute of Science and Technology, and he will be telling us about zero to Earth field NMR, relaxometry, and spectroscopy via atomic sensing.
Did we get it?
Yes, it looks
okay. Good. Thank you, Thomas. So yeah, firstly, thanks to you and all of the organizers for inviting me to speak at this fantastic meeting. It's run like clockwork. So this talk is about our work on detecting NMR using atomic vapors. And my main message is to show you some of the techniques that we expect to use in the near future with parahydrogen, and to benchmark what is possible before we start to introduce parahydrogen. Now, some of you may know that magnetometers have been used in some form by the NMR community for decades now, but they're still considered very exotic and not been widely adopted, especially as they're highly evolved in other fields of sensing, like biomagnetism, in applications like MEG and MCG, which are medically relevant. And speaking personally, I learned about these magnetometers in my early postdoctoral career in detecting NMR at zero field, which is a very beautiful experiment studying NMR without Larmor precession in systems of strongly coupled spins with unusual symmetries, narrow lines, and some very interesting engineering. And that's really all they seem to be known for at the moment. So in this talk, I want to convince you that magnetometers should be more mainstream in NMR. And I'd like to attract you by demonstrating our system, which is allowing a widely tunable NMR detection over a range of magnetic fields up to the Earth's field, so about 10 kilohertz of Larmor frequency, without any large sensitivity loss. The switching between and stabilizing between fields is rapid, about 100 milliseconds. And I will be explaining how we do NMR inside magnetic shields up to continuous fields of about 20 millitesla. And then I will give some illustrative applications of field cycling, which are not related to parahydrogen enhanced NMR, but we'll see what we can introduce along the way. So as we heard in many of the previous talks, many NMR experiments derive their parahydrogen enhancement at low magnetic field, and Saber sheath being one example, which exploits anti-crossings between hydrogen and nitrogen-15 at microtesla fields. But most of the time in applications, we are detecting NMR at a high magnetic field. And that's usually for very good reason. High frequency inductive pickup is very sensitive, and we can benefit from chemical shift resolution. And more often than not, high field NMR instruments are what we have in our laboratories. So we simply use them. So in these cases, we have to switch the field. So we have to move the sample between the low field and the high field. And we can do that either by some kind of mechanical movement, shuttling, or we can switch the field of the same magnet by some electrical means. But sometimes this can be a nuisance. So what about the cases where we cannot switch field, or at least reliably switch to and from low field and fields of several Tesla? Perhaps we don't need chemical shifts, or we don't even have a high field magnet to start with. So do we have an alternative to high field in these cases? Maybe there's also some other kind of incompatibility. One I can think of, again, in the parahydrogen field, is that you don't want to cycle your system through certain magnetic fields because this introduces additional perturbations which are unwanted. And of course, field switching incompatibilities, whether they're fundamental or practical, are not unique to parahydrogen enhanced NMR. So many other NMR phenomena depend on field, and I'll leave you to read these at your leisure. But Later on in the talk, we'll revisit measuring relaxation as a function of magnetic field in the ultra-low field regime to probe motions of molecules on the timescale of surface interactions, which is on the microsecond to millisecond timescale. So let's talk about optical detection and what's possible. Well, schematically, at least, NMR as detected by optical magnetometers is a surprisingly simple system. We can represent it something like this diagram. We want to measure NMR from an ensemble of nuclei, and we can do that by encoding the nuclear spin state in a beam of light, which is then photodetected. Not directly, but we use another ensemble of one electron, a spin half atoms as an intermediate. And a discussion of how this system behaves could go on for some time. So I need you to accept at this stage that we can measure, using this light beam, a projection of the atomic angular momentum using linearly polarized light. And so this is an effect called optical rotation, which I believe appeared in one of the previous talks for this box here being nuclear spins, but here we're talking about atomic spins. So we measure an angle of rotation after the light has passed through the atoms, and that's caused by the angular momentum of the atoms parallel to the light beam. So if the probe light is, say, along the x-axis, then we measure the rotation proportional to the component Sx of the atoms. So this is the measurable quantity. And then from this point, as we're all NMR experts, we can deal with the rest of this problem, albeit with some further outlining of the approximations and the knowledge of the initial conditions. So one of these is that the atoms and nuclei, being in different containers, are far enough apart that we can treat the coupling between them classically. And so the atoms simply see a magnetic field produced by the overall sum of the magnetic moments of the nuclear spin system, so the overall magnetization of the sample. And then we can think of the nuclei having any time dependence that we like, but for this example, let's assume that we have a rotating field in the XY plane due to Larmor precession of the nuclei about magnetic field applied along the z-axis. So we'll look at how the atoms respond to the total field, which is the applied field, and then that due to the nuclei. And then finally, there's a second laser beam to polarize the atoms along the z-axis, and that's by optical pumping effects. So we can therefore write down some block equations, and we can find a solution to this block equation simply using the transformation to the rotating frame. It's something I'm sure everyone is familiar with. And we get a result which looks like this. So what's the meaning of this? So we get an expression telling us how strongly the atoms respond to the nuclear RF field as a function of B in blue, as a function of the background magnetic field BZ in black. And then initially the result looks very discouraging. So look at this denominator term going as BZ squared. So the denominator says that the amplitude of the atomic response decreases with the strength of BZ, Lorentzian, in fact. So if this is the setup here, where you have the NMR sample and the atomic sensing spins in the same magnetic field, we can only expect a very limited range of detection fields. And in practice, that's only about 1 or 2 microtesla, shown by this series of spectra for proton precession in water. And of course, the signals appear very strong, even for such a small volume of water, 100 microliters. But this is very far away from the frequencies which are involved in more conventional NMR sensing. So on the other hand, well, we can look at this equation more closely, and if you recognize that the term here in brackets multiplied by B is simply a difference in Larmor frequencies of the atoms and the nuclei, then we could say this system is over-constrained. So why not have different magnetic fields at both the atoms and the nuclei? So say something like this. And in that case, we could make this denominator disappear if we match these fields accordingly. And in practice, that's quite achievable. So one can localize a field at the nuclei simply by adding a solenoid coil to the apparatus. That produces a strong interior field, which the nuclei see, but little to no exterior field that the atoms see. So let's get rid of these terms which are crossed out. So with that, one can obtain a sensitivity which is broadly independent of the field. And here below, again, that's illustrated for a sample of water. And it works surprisingly well, in fact, without any additional shimming of the solenoid. You simply put a single layer solenoid, and that allows one to tune up to, say, two orders of magnitude more than was previously possible. And so you see a signal to noise that's comparable in these two spectra, even over a 2 order of magnitude difference in field. So before going further, I'd like to stress that this expression up on the top for the atomic response relies on treating the atoms as spin half. So this is not true at arbitrary fields, especially high fields where the hyperfine coupling starts to become important on the atoms. And in our system, this approximation breaks down around 10 kilohertz of proton frequency, where we notice a rapid drop in the T2 of the atoms. But nonetheless, this is still a useful improvement of the detection range. And there's one more coil here, by the way. So a very important one, that's a coil to prepolarize the nuclei. And in that case, in our case, that's done at about 20 millitesla. And as a side note, well, that, as we know, that's well above the field used in proton saver. So that's worth thinking about. We use a cooling system for this solenoid, since the coil deposits about 25 watts of heating when it's energized. And that keeps the sample temperature very close to ambient, which again, by the way, is very close to, is very good for the chemical dynamics of saber, and it's also good for biosamples. And then below, I wanted to show a demonstration of what is possible without any parahydrogen enhancement. So here are some proton precession spectra for water in a single orange fruit vesicle over here on the left, which contains about 10 microliters of orange juice. So even after only accumulating about 10 scans, and one can observe signals, but note the polarization. The polarization is only 1 part in 10 to the 8, around 10 to the 12, 13 polarized spins. So I think it's very exciting to think about the possibilities if this were enhanced by parahydrogen, even if only very moderately, by a factor of 100 to 1,000. Let's switch over to a live demo then. So we're now looking at, we're hopefully looking at the user interface screen for our spectrometer, which is running somewhere else in the building, and that we can access over Wi-Fi, so we can do it from home or wherever we like, from the beach in Barcelona, or from our own home. This is already showing a NMR signal at about 80 hertz. This is for a water sample, 1 milliliter of water prepolarized at the 20 millitesla field, and this is a single scan. So let's simply demonstrate the aspect of being able to switch the field at will. We could think of a random number, but I think it's more fun to ask Thomas. Thomas, tell me a number between, say, 100 and 1,000.
How about 555?
Okay, 555. So I'm going to type that into the box here on the user interface, and then I'll press run. And while it's running, so it's polarizing the nuclei for 4 seconds at 20 millitesla, and then we have about another 4 seconds worth of acquisition. And okay, up pops. There's some scaling here due to some filtering which is used. Here's our signal here at 555 hertz. So I think that's quite fun. What's going on when I type in this new frequency is then the user interface is using all the calibrations that we've done to calculate what magnetic fields need to be applied in all of the coils in order to tune the magnetometer to the NMR frequency that we want to measure at. Let's do another one. Since it's fun, let's go 363. Okay, and there we go. So single scan NMR with arbitrary choice of Larmor frequency in this range of low magnetic fields. So let's go back to the presentation. Let's see some applications. So our motivation originally was to probe in this field range relaxation due to molecular absorption on surfaces where correlation times are, say, very slow compared to other molecular dynamics. And as we well know, interesting relaxation dependence is expected for Larmor frequencies around the inverse correlation time of those processes. So that's going to happen at Larmor frequencies around the sub-Earth field range. The current problem of characterizing these slow motional correlations is that conventional equipment for NMR relaxometry can only go so low in magnetic field. So most of the time, not below Earth's field, so about 5 to 10 kilohertz of proton frequency. So we're still outside that millisecond dynamics range. That's really a methods problem. So fast switching electromagnets, which can reach up to 1 Tesla to profit from high field polarization and inductive detection, are too strong to be passively magnetic shielded. And therefore it's hard to shield out the Earth's field in a reliable way. So in many cases, like this porous alumina system, we see a very limited and often poorly dispersed part of the relaxation curve. And we're often left wondering what happens down at lower fields. So what is the shape of this curve? Does it plateau? What frequency does it plateau? Can we extract a correlation time from that? Are there additional mechanisms that come into play, and what do we learn from these? But with the low field detection approach, then this relaxometry experiment can be performed entirely inside the magnetic shield. So we eliminate any interference from the Earth's field. And so we recreated this experiment by measuring T1 against field for the hydrocarbon decane in the same alumina sample. And the result is quite striking, I think. So on decreasing the magnetic field, the T1 rate increases logarithmically, and it keeps on increasing until fields that are 2 orders of magnitude lower than the Earth's field, and we start to see some evidence of a plateau around 10 hertz of Larmor frequency. And then, not to go into the detail, but this behavior is highly characteristic of so-called surface diffusion, where the molecule is experiencing some form of restricted rotation near the pore surface. So rather than some kind of truly random correlation function, there's some anomalous correlation function that results in this scaling of T1 and spectral density of the motion with frequency. So we think there's a lot of insight into both material structure and the dynamics from this information. We're also able to measure T2 down to around 100 hertz frequencies. We run into some problems here, which is that of excess noise down in the below 100 hertz region. So this is somewhat in progress. It's indicating perhaps some plateau in T2. If you're expecting that T1 tends to T2, maybe you're disappointed. But we're still measuring T2 down in this field range. So I'll skip further discussion of that in the interest of time. Very quickly, here are the same T1 data points in the context of some other samples that we can measure. So relatively high concentration of the radical tempo in water and then pure water. And both of these systems, one observes a plateau in the relaxation rate as a function of field. And then some indication of the experimental limits. So one of these is that at high relaxation rates, we're suffering from a dead time of several milliseconds before measurement of the NMR signal. And that's because the atoms themselves are polarized and they generate their own magnetic induction signals at the same frequency of the nuclei, so they're hard to filter out. But perhaps with some optical techniques, one could eliminate those two. We have not gone up beyond 100 millitesla in field inside the magnetic shield. That's mainly because we're worried about irreversibly magnetizing the shielding material and also simply power dissipation concerns. But then this region here, which we were focusing on, is well outside the working range of more conventional relaxometry techniques. So I'd like to finish very quickly by addressing spin systems that have heteronuclear couplings, because as we know, as we've seen in many of the talks, these can be observed down to even zero field. As it turns out, the field range that we're talking about here, say from 10 to 100 microtesla, is the range where hydrogen and fluorine-19 couplings transition from weakly coupled to strongly coupled. So on the left here, at 5 microtesla, we're in a strongly coupled regime, and we can measure a spectrum where peaks resemble a near zero field spectrum, at least centered about the average frequency. And then going over to the right, we increase the field and we start to see peak patterns that resemble a high field fluorine triplet and a hydrogen quartet. So this is very nice, but why would this field variation be useful? So some suggestions, which is again work in progress. In the context of parahydrogen enhancement, many people during this meeting have said it would be nice to detect NMR signals at the same field at which the enhancement takes place. So we should be able to provide that capability. In more general context, we could look at improving resolution, either compounds in mixtures. So say at one magnetic field, then there are some resonances which overlap, but then they wouldn't overlap if you move to a slightly different field. We could also think about which of these fields allows a more accurate or precise estimation of the J coupling. So if we translate these spectra above, if we fit the line frequencies to a J-coupling and then plot that against field, we can observe the uncertainty as a function of field, and there are some trends here which can be identified, like gradient broadening, which increases the line width towards the higher field end, and then a more limited number of transitions at the low field end, which provides less information for the fit. And you could, with some justifications, try and take the entire data set and fit a single J coupling to that, and hope to obtain some very precise value for the J coupling. And if you want to know more about NMR spectra in this strong to weak coupling regime, I highly recommend this paper by Stefan Appel, which was published as a theory paper with some Earth's field NMR measurements about 10 years ago. But now we're getting to the point where we have capability to explore this whole field range experimentally. I think that's very exciting. So then in summary, I want you to take away the message that you can already do a lot with low field NMR detection using magnetometers. So some of the features of the setup that we have some rapid and arbitrary tuning of a wide frequency range, which is very interesting to us who are also interested in parahygiene enhancement with an appropriate range of magnetic fields. And then we're thinking about other applications beside parahygiene enhancement. So with that, I'd like to thank the people who are involved in the work. So especially Sven, who did all of the experimental work. He's a fantastic graduate student to have, and Morgan, my mentor here. We have lots of funding available. So if you find this work exciting, then please get in contact. So I hand back to Thomas for the questions, and thank everyone for listening.
Yes, what a wonderful contribution. Thank you so much, Michael. We're just about out of time. I'll just restrict it to one short question. Is it possible to use multiple detectors to improve the signal, for example, as in multiple channel RF coils?
Yeah, absolutely, that's possible. So the magnetometer ideally should be matched to the size of the NMR sample, so that one improves the pickup efficiency, and you want to minimize the standoff distance between the sample and the sensor, since unlike say an RF pickup coil, which is used in conventional NMR, this is not a concentric system. It's one box of atoms next to one box of nuclei. However, okay, you still have some free space, so you could have your box of nuclei and then you position around that many boxes of atoms. And I think something like that is going on in the Mainz lab.